Hi again. Let's turn to how to compute whether two words are similar or not. And we'll start in this section with methods that use a thesaurus to compute word similarity. So where synonymy was a binary relation, two words are either synonymous or they're not, we often want a looser definition of similarity or distance that says two words are more similar if they share more features of meaning, without requiring that they be absolute synonyms. And similarity, just like synonymy, is a relationship between senses, not between words. So we don't say that the word bank is similar to the word slope. We say the sense 1 of bank is similar to the word fund, actually sense 3 of fund, but it's actually sense 2 of bank is similar to slope. Remember, we had two senses of bank. So even though technically similarity is a property of senses, we'll find ways to compute similarity over words as well, either by taking the max similarity between senses or summing or various ways. Now, word similarity plays a role in lots of applications. You might want to know if two words are similar to grab a set of synonyms or similar words for the query someone asks in information retrieval, or for the answer in question answering. Lots of times the translation of a word, you'll have to look for similar words to help find a translation. Essay grading, where students write an essay and you need to know what the similar words are to the correct word for the concept and so on. This comes up a lot. And in all of our applications for word similarity, we often distinguish technically word similarity from word relatedness. So a similar word is a near synonym, but a related word can be related in any way. So car and bicycle might be similar. Maybe they're not synonyms because car and automobile are synonyms. Car and bicycle are not quite so close, so they're similar. But car and gasoline, clearly related. Gasoline is something that goes with cars, but it's not similar to cars in some way. So we're generally here looking for similarity, but occasionally some of the algorithms will give you instead words that are related, and that might or may not be useful depending upon the application. There are two classes of similarity algorithms. Thesaurus-based algorithms we'll talk about in this section. Are words nearby in the hypernym hierarchy? Or do words have similar glosses? We'll use the hierarchy or the glosses as ways of defining similarity. And distributional algorithms that we'll talk about in the next section. Do words have similar distributional contexts? So the simplest of the thesaurus-based similarity algorithms is called path-based similarity. And I'm giving you a little picture here of the word net hierarchy. And here we say two concepts, two senses or syncepts, we'll call them concepts for now, are similar if they're near each other in this thesaurus hierarchy. By near each other, we mean have a short path in between them. And we'll define path length somewhat unusually. We'll say a concept has a path length 1 to themselves and 2 to their nearest neighbor and so on. So the concept nickel has a path length 1 to nickel, 2 to coin, and 3 to dime, because it goes 1 for nickel, 2 to coin, 3 to dime. And the path length between nickel and coinage is similarly 3. And to all the way up to money is 6, to coin, to coinage, to currency, to medium of exchange, down to money, and so on. And nickel's even further from Richter scale, goes all the way up to standard, and then down to Richter scale. So the path length formally is 1 plus the number of edges in the shortest path in the hypernym graph between the sense nodes C1 and C2. Now we can turn path length, which is a distance metric, into sim-path, a similarity metric, simply by taking 1 over the distance. So we'll take the path length and invert it, and we get a similarity metric. And we can turn the sense-based metric, sim-path is a metric of similarity between two senses or concepts, C1 or C2, and turn it into a metric between words by taking the maximum similarity among pairs of senses. So for all senses of word 1, and all senses of word 2, I take the similarity between each of those word 1 senses and each of those word 2 senses, and I take the maximum similarity between those pairs. And that's the similarity between the words. So returning to sense-based similarity, we've got our metric now for path-based similarity, 1 over the path length. So between nickel and coin, we have a path length of 1 over 1 plus 1. Remember, we're adding 1 to the number of edges, so it's 1/2 or 0.5. Between fund and budget, similarly, 1 over 2 or 0.5. Between nickel and currency, we have 1, 2, 3 edges, so 1 over 3 plus 1 or 4 is 0.25. between nickel and money. Now we have 5 plus 1 or 6, distance 1 over 6. Similarly between coinage and Richter scale, or a similarity of 1 over 6. Or for that matter, between nickel and standard, also 1 over 6 or 0.17. Now there's a problem with this basic path-based similarity, which is that we assume that every link represented a uniform distance. Nickel to money somehow seems to us it ought to be closer than nickel to standard. And that's because nodes that are very high in the hierarchy are very abstract. We'd like a metric that says that nodes whose only link is going all the way up to the top of the hierarchy, those are probably not very similar words. And to do that, we'd like to represent the cost of each edge independently. The most common solution to this problem is the use of information content similarity metrics, first proposed by Resnick in 1995. And these define a concept P of C, a probability of a concept C, as the probability that a randomly selected word in a corpus is an instance of that concept. And formally what I mean is there's a distinct random variable that ranges over words associated with each concept. So every node in a hierarchy has this random variable. And for that concept, every observed noun is either a member of that concept with probability P of C, or not a member of that concept with probability 1 minus P of C. So every word is a member of the root node, which might be called entity or might be called something else in different versions of WordNet or your own hierarchy. So that means that the probability of whatever the root node is 1, and the probability of nodes right below the root node are going to be very high, and the lower you get in the hierarchy, the lower the probability. Let's see how that works. So here's a little piece of a hierarchy. We've got entity here. There's actually something above this hierarchy in the top. And then we have entity, then we have down to geological formation, and then some leaf nodes, hill, ridge, grotto, coast, and so on. And we're going to train information content similarity first by training a probability, P of C. And every instance of a word like hill counts toward the frequency of all of its parents, of itself obviously, but also natural elevation, geological formation, all the way up to entity. So if we define the concept words of C is the set of all words that are children of node C, I should say plus C itself as well. So the words of natural elevation are hill, ridge, and natural elevation itself. The words of geological formation are hill, ridge, grotto, coast, shore, cave, natural elevation, and geological formation itself. And now we can take, for any concept, we sum over all the words of that concept, so itself and all of its children, sum the counts of all those words, and then normalize by the total number of words in the corpus. And that tells us the probability of the concept. So the probability that a random word will be an instance of that concept. Once we've computed these probabilities, we can associate them with a hierarchy. So here's probabilities computed by DeKong Lin. And so now we can say that the concept coast has probability 0.000216, while the further up we go in the hierarchy up to entity, we have a probability of 0.395. And whatever in this particular version of WordNet was above entity will have probability of 1. Now that we have probability, we just need two more things. We'll define the information content of a concept as the negative log probability of that concept. So we're just following the information theoretic definition of information there. And we'll define the lowest common subsumer of a node as the lowest node in the hierarchy that subsumes both of them, very naturally. So the lowest common subsumer of hill and coast, think about that. Geological formation. The lowest common subsumer of coast and shore, shore. Now, how are we going to use this information content as a similarity metric? There are a number of methods. The Resnick method, we say that the similarity between two words is related to how much information they have in common. The more they have in common, the more similar they are. For Resnick, we just say what's in common between two words is the information content of their lowest common subsumer. If I have two concepts, what's in common between them is the thing that they share as their inherited thing in common. So if I just measure the amount of information in that, that is in fact what they have in common. So the negative log probability of that least common subsumer, that's their similarity. So we'll define that metric, the Resnick similarity metric, this way. An alternative metric for dealing with information theoretic similarity is the Lin metric. As with Resnick, the more two things have in common, the more similar they are. But now, the new intuition, the more differences between A and B, the less similar they are. And we measure commonality by introducing the predicate common, which is a proposition stating the commonalities between A and B, and IC, the amount of information contained in that proposition. And to measure the difference between A and B, we say that the total description of A and B, the sum of everything we know about them, is the sum of the commonalities plus the differences. So to get the differences, we can take the description and subtract out the commonalities. So roughly speaking, A and B are more similar if IC of common is high and IC of description is low. So the Lin similarity between two concepts A and B is higher when they have more in common, less when there's a lot of other things about them that they don't have in common. And Lin modifies Resnick in defining the information content of the commonality of the two as twice the information of their lowest common subsumer. And so, given two concepts in a hierarchy, the Lin similarity is 2 times the log probability of their least common subsumer over the sum of the log probabilities of the two concepts, the total of the description that we know about the two concepts. Let's look at an example in our small sample hierarchy. We want to know the Lin similarity between the concepts hill and coast, and we look at their lowest common subsumer, geological formation. We take twice the log probability of that, divided by the sum of the log probabilities of the two items, hill and coast, and that gives us, for the Lin similarity between hill and coast, as 0.59. Now a final thesaurus-based similarity metric is called the Lesk algorithm, after Michael Lesk, who invented it. It's often called Lesk or extended Lesk. And this method, instead of using the hierarchy, looks at the glosses of the words in the dictionary or thesaurus. And the intuition is that two concepts are similar if their glosses contain similar words. So the two WordNet words, drawing paper and decal, have lots of similar words. Paper that is specially prepared for use in drafting, transferring designs from a specially prepared paper, blah, blah, blah. And we have here the words specially prepared are in common and paper in both definitions. And so for each n-word phrase that's in both glosses, the Lesk algorithm adds a score of n squared. So paper is in both glosses, that's a length 1, so we'll add a score of 1. Specially prepared is of length 2, so we'll add a score of 2 squared or 4. So the total Lesk similarity between drawing paper and decal is 5. And in fact, with most versions of Lesk similarity, we don't just look at the glosses of the two words, we look at the glosses of the words, their hypernyms, their hyponyms, and so on, and we add all that up. So it's a sum over all the words, or sometimes a max over all the words of their similarity. So in summary, we've seen 3 classes of thesaurus-based similarity. Path length similarity, where two words are similar if there's a short path between them in the hierarchy. Information theoretic similarity, we've seen 2 methods, Resnick and Lin, and there's a third one called Jiang-Conrath. So these are the information theoretic similarity, where we're looking at the least common subsumer of a node, measuring its probability, turning that into an information measure. And we've seen Lesk similarity, where given 2 concepts, we take the gloss of them and compute the overlap in words with this kind of weighting that we talked about. Or we might just look at the glosses, not just of the words, but of some words in relation to those concepts, like their hyponyms or hypernyms, and so on. And we sum all that up over a specified set of relations. And that gives us the Lesk similarity, or extended Lesk similarity. There are lots of libraries for computing these various thesaurus-based methods. In Python, NLTK has methods, and there are Python-based tools like WordNet similarity, and there's even a nice web-based interface so that you can check out the similarity between 2 words based on different methods, and you can go take a look at all of these. We evaluate similarity, like many other NLP algorithms, in 2 different ways. We can do intrinsic evaluation, where we look at the metric itself and say, how similar is the numbers this metric gives to what humans would give on some similar task? So I get a similarity metric for two words, and then I get humans to give me a number. How similar are these two words? And I compare those. So that's intrinsic evaluation. More functional is extrinsic or task-based end-to-end evaluations, where I have some application, I put my similarity metric in the application, and I see how well it improves the application. And that application could be word sense disambiguation or spelling error correction or essay grading. A common simple extrinsic test that's used is taking the test of English as a foreign language, or TOEFL, multiple choice vocabulary tests. So here we have questions like levied is closest in meaning to which of these four words. And we can simply take our similarity metric, compute the similarity between levied and imposed, levied and believed, levied and requested, levied and correlated, and see if our metric returns the right answer, the most similar word, or the correct answer is imposed. So thesaurus-based methods for word similarity are a useful way of telling if two words are similar. They're very functional in languages like English, where we have lots of thesauruses either for general text in WordNet or for medical text in Mesh. They work less well when we're working in particular genres where we might not have the right information in the thesaurus, or in languages for which thesauruses are not as available. And so for those applications, we'll turn to the distributional methods that we'll see next.